And we are now live. Hello, everyone. I know people will be joining over the next few minutes. Please feel free to introduce yourselves to when you come in. We want to hear who you are and where you're from. It's always fun to hear that. Oh, Greece. I need to do that to all panelists. Ooh, New Hampshire, France, Cape Cod, Holland, Egypt. 7:57, does that mean he's in the air right now? Virginia, Arizona, Illinois. Oh, everybody, if you want all people to see it, please put the 2 to all panelists and attendees. California, Italy. Someone suggested that since we have such a broad variety of people coming to these things from all over the world, that we should make up a map when the webinar series is done. So we're going to do that and post it after we've done all of these things to just show how much of the world we've covered. Belgium. Oh, I missed one. Arizona. Nebraska. Oh, Maryland. It's always interesting to see just how many different places, even the people from various states sometimes are from places that I have never heard of. Like I've never heard of Ocean City before. Virginia, Mexico City, Wisconsin. There's a Salem, Wisconsin. I did not know that. So Salem, Oregon, and a Salem, Massachusetts. I wonder if there's something about Salem that I don't know. I know that there are lots of places, like there's a Paris in just about every state, but I don't know why there would be a Salem in so many places. Wow, Siberia. That might be the first time I've seen that. France, California, South Africa, Massachusetts, Finland, Spain, Quebec, multiple people from South Africa. UK, Germany, Brazil, cool. Lots of apparently RLI reservers from Spain who are interested in this particular webinar. I wonder why. England. Give everybody a couple more minutes before we start. Ohio, okay, we'll give people just one more minute here, and then we'll get started. Okay, let's get started. Hello and welcome everyone. The first thing that I would like to do is welcome you to the Short Period Pulsators webinar. Your host today will be Eric Heintz, Jerry Simolik, Richard Berry, Nolan Sadaway, and Sol McLean. We are supported by two very special sponsors right now. One of them is Astro. Oops. Sorry, I will get back to that in just a second, but I have to read my little blurb and it's not showing up on my screen. So Voice Astro provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools to learn how to perform observations, conduct research, and publish their results in scientific journals, like the Journal of the JVSO. And I would also like to thank our new sponsor, ATIC Cameras. ATIC Cameras manufactures a diverse range of quality astrophotography cameras and accessories, along with a range of free software to help you maximize the output of your equipment. For more information, please visit their web pages. As always, links to our sponsors can be found in your post-webinar email. Now, just a couple of things before we get started for real. The first is that there are two ways that you can talk to people or talk to us. One is through the chat, and the other is through Q&A. We ask that any questions that you have for the speakers, please address through the Q&A portion, which is right here. This makes it easier for us to figure out where the questions are, and so we don't have to find them or cycle through the chat for things. So if you want your question answered, please ask it through Q&A. The second is that if you are having any technical issues with sound, go to the little microphone. There's a little up arrow there. Click that and then go under audio settings. Make sure that your microphone or speaker is the correct one. And anything else, please go through audio settings. Unfortunately, there's nothing we can do on our end for you in that regard, but we hope this helps. And without further ado, I think it's time that we start the webinar for real. Our first talk will be by Eric Heintz. He will give us an introduction to the section and also talk about why we want to study short period pulsators. Let me stop my screen share real quick.
Go over to mine. Let's see. Gotta get the right one here.
No worries.
Okay. Well, let's see if it will come up. There we go. Okay. Well, welcome to everybody. I didn't see anybody else from Utah on the list there, but I'm up in the observatory here on the BYU campus, and welcome everybody. And try to give you a little background here on short period pulsators and the wider variety of topics you could become involved in, and hopefully will become involved in and help us out understanding these objects. So let's kind of walk through here. Kind of historically, if we look at our variable stars, starting with Myra with the long period variables and working into when the Cepheids came, we kind of start over there to the right-hand side, and then we come into the instability strip region here, and then the Cepheids, discovery of the Cepheids, the longer periods of the instability strip, and then the Ariel down below. And that is a set that have been observed for a very long time of objects. But what we'd like to also share is that there are an awful lot of different pulsating variable stars out there, a lot of different opportunities to become involved based on your equipment and the ability to do some really fun things. I use some of these stars for teaching, and it's fun to have things that people can see in a single night. And so let's look at a broader perspective of the short period pulsating stars here, where we're dealing with the wide range here. So if we expand on our instability strip over here to the right, and we had our Cepheids nicely up here, the Ariel down towards a little bit lower on the strip. But down at the bottom of the strip, we can add in some more pulsators that are main sequence stars, so actually burning hydrogen. And we have delta Scooties down here. And within that, we could get some SX Phoenicius stars. And you'll hear about one of those later. Some Rho AP is another subgroup that's within here. And then just to the side, right on the edge of the instability strip, are a group called Gamma Doradus stars. And if you want to have a really fun time, there are some hybrids between Gamma Doradus and Delta Scooties that can drive you nuts trying to analyze them, because they're kind of trying to do two things at once. If we slide up the instability, or sorry, up the main sequence here, a little higher in the graph to this blue area, another set of short period pulsators are beta Cepheids. These are not related to the Cepheids. One of the prototype stars is beta Cephei. You might see a very few references to beta Canis minoris instead of beta Cephei, but the beta Cephei name has become more established. The interesting thing here, I'll show it in a minute, but the Cepheids are a longer period pulsation. Aralaris are a little quicker. Delta Scooties are quicker than that. The beta Cepheids kind of look like the Delta Scooties. And then there's a set of slower pulsating B stars. And if you want to have fun, a lot of times with instability strips here, you see this dashed line. If you just keep going down, you'll actually encounter another group down here. There are some pulsating white dwarfs as well. So when we talk about short period pulsating, there's a lot of different possibilities to study that provide different information about the stars. And some of that I'll mention in just a minute here, a few minutes. And so then there are a few that new classes that might be coming out that are currently being defined that would fall within the short period pulsating category. So there is an awful lot of targets out there to chase. So if you want to be involved, if you want challenges, so some of these are much more challenging to observe, particularly the pulsating white dwarfs, then maybe we can provide you with some adventures in the future, or let you bounce around and find the stars you like to work on. So just a little bit background on pulsation as a mechanism for a variable star. So something changing in brightness here. So if we talk about the brightness, talking about the luminosity, you'll see that in a lot of graphs. And in this case for stars, fairly straightforward. It's the radius of the star squared. So the bigger the star is, the brighter it is. And then if we go to the temperature, temperature to the fourth power. So temperature is very dominant here. So very strong. But the temperature gets hotter, the star gets brighter. Cooler gets cool. It's a little less bright. And then these two together, some combination is what's going to provide the brightness of the star. In the case of our stars, the pulsating, at least this is true of all pulsating stars, but let's stick to the short period ones here. We have an instability. Well, I'll mention a little bit of that in a moment, what might lead to this instability. And so in this case, both the radius and the temperature are going to change for these stars over time. And these are going to happen for the most part in a regular pattern. So it's going to repeat over time. Some stars have been observed for hundreds of years already. And so if we look at this, some battle between the radius changing and the temperature changing is going to produce a different brightness. If we plot this over time, we're going to generate a light curve. So just plotting the brightness as a function of time. And then we can analyze that change in brightness to tell us different things about the stars. And then if we look in the different areas, the different groups of stars, you'll see that there is each type of object has a very different, distinct combination of amplitude and period. So like I said, the Cepheids are the longer period, Aralaris shorter, Delta Scooty shorter, white dwarfs, very fast pulsators. And this all goes back to the internal structure of the star. which is something, one of the reasons why we really want to study these objects. It's one of the, I'm getting ahead of myself. I'll mention that in a few minutes. Just to give you an idea, some light curves. I'm biased a little bit. I've been doing delta Scooty work for 35 years now. It was actually my project when I was an undergraduate working on delta Scooty. So they're kind of my favorites. But the nice advantage here of plotting a period across the, or sorry, time across the bottom, luminosity or flux or magnitude up the left-hand side here, and then just plotting these over time and being able to see these stars change. It's really kind of exciting to actually physically see something changing on a fairly short timeline. You don't have to wait long to see these things happen. And that's kind of what makes them fun, makes them enjoyable. And just to give you kind of a quick rundown, there is a lot of overlap here, so it's kind of a little hard to do these right here. But we're talking about 2-day Cepheids having a longer period. Then we get Ariel kind of the 0.2 days, so 5-hour-ish timelines up to a day or so. Delta Scooties can get really quick. Gamma Doradus are kind of got a little bit of both of these. Beta Ceps look a lot like Delta Scooties. Then you notice white dwarfs. If you really want a fun challenge, get down here on 30-second periods. That might be a good reason to go to the detector talk webinar later to hear about CMOS, where you can actually handle some of these things. Just really quickly here, I don't want to take a real long time, but with stellar pulsation, this really, there's a lot of physics built into this. When I teach this in a graduate environment, it's usually the better part of 2 weeks trying to go over the topics. I'm trying to boil this down to the very simple part of it here. So basically, it comes back to a term called opacity, which is effectively how much light is blocked. If you look at kind of the figure off to the right, you can see we're blocking a lot. Some light's coming through, and then if we get all the way over, more light's coming through. So if we block the light, there's going to be a push outward, push the star to a larger size. If the opacity, if we let the energy go through, so if it's transparent, say like glass, it's going to just go right on through. And so what we wind up with here is the idea of a driven oscillator. So we have something like somebody on a swing. If you want them to keep swinging, you're going to have to push them each time they come back. That's what's kind of happening here with the pulsating stars. The battle between a pressure outward, gravity pulling in, and this is going to lead to that steady oscillation. And that's true of all these objects. The source is just a little bit different. I was debating how technical to get in some ways. I know some people like the technical side, but it can also get a little intimidating. So this is kind of the process that you go through. I might just skip through this and let people ask later if they're really interested in the real details here. It's a funny combination of effects that need to drive these stars. Most of this is an ionization issue. So one of the questions that sometimes comes up is, well, if this happens, why don't all stars pulsate? And it's because of where these regions are. So I think I'm just going to, the more I've thought about this one, the more I think it's a little too technical. So we'll kind of go on. But you can look up this opacity mechanism here, this name, to get an idea of what's going on. But just in this idea of the ionization zones and why we only get certain regions pulsating. When a star is too hot, so as the stars get hotter, basically the region that can cause pulsation is higher or is near the surface of the star where it becomes low density, and we can't drive the low density material well. So that's what's going to generate the blue edge of the instability strip. as the layer gets deeper and deeper as we get to cooler stars, we basically, one of the processes here is that the energy is carried by the photons. When we get this layer too deep in the star, we actually get into a convective region, and so that's the red edge. And if you're interested, the hydrogen and helium are really what drive the Miras. An H2 is, or helium-2, sorry, is what drives the instability strip. And if we get up to the beta Cepheids, it's actually an iron ionization. So around different parts of the instability strip, we have different driving mechanisms. So that tells you there's a lot of information. There's a lot of physics we can study by studying these objects. And we have to watch them over time. We have to watch them for long periods of time to see this happen. So basically at that point is your challenge to go out and help us observe these objects as much as possible. Now, why do we want, what's some of the stuff we can learn by studying them? And I'm going to switch over to a set of slides that were generated by Horace Smith, but Horace couldn't join us today. So he sent the slides to me to go over with you. And so what are the goals of the short period pulsator program as a whole? Why in the world do we want to study these things? Why do astronomers spend their time working on these things? Why do people make a career out of studying these things? Well, historically, we really go back to 1912 with Henrietta Leavitt and the discovery that the Cepheids, she found a number of Cepheids with different periods, so the time it took to pulsate was different. And then comparing this to the brightness, the over average brightness, she found a relation that the longer the period, the brighter. And so if you could measure the period, you actually knew how bright the star was. This became the first of the first rung of the distance ladder in scaling the universe. So they're extremely important objects, and understanding them is important to make sure that when we're using them as a period, as this distance indicator, that it is a good system, that we don't find something that it won't invalidate it, but we need to understand the stars better. And these are used for star clusters into galaxies, and then other techniques take galaxies to the full scale of the universe. But this is one of the very bottom fundamental rungs of scaling the entire universe. And what she found here, just looking at, so absolute magnitude on the left, period along the bottom, and you see these nice tight lines. So we have the classical Cepheids up here, the type 2 Cepheids down here broken into four groups, sorry. And so you're kind of looking that there's if you know which group you're in, it gives you a very good idea of, if you can measure the period, what's the absolute magnitude. You can use that then to find out how far the object is. Related to this in a slightly different way, the RLRs are also used as a distance indicator for a little bit closer objects. And actually the delta Scooties also have a period luminosity relation, but they're kind of faint, so they don't work well to give us long distance measurements. So here are kind of the four main areas of why to study the short period pulsators, and why we might need some extra help in this subject a little bit. One is just determine periods, light curves, period changes. One thing about these stars is the periods don't necessarily stay constant, they can change. And so how do we monitor that? How do we, and then what is that showing us about these objects? A second one is Astro Seismology, and that, actually he misspelled that. I can't believe he misspelled that, sorry. There's an E in here. It's not Astro, it's Astro. And some of these stars don't pulsate in a single period with a single clean pulsation period. They pulsate in a lot of periods. And by using those, we can look at the inside of the star, which is kind of interesting. Another thing is there are a lot of large surveys out there that are existing right now. This is something we'll talk about later. After we go through a couple case studies, we'll actually come back and show something about a topic called Cadence and how these large surveys can sometimes get the wrong answer for a particularly very short period variables. But being able to follow up on things like the large LSST, I always get the letters backwards if I do it wrong. So something like the LSST, the test satellite that's flying, things like that that generate variable stars, new variable stars to study that we can follow up on. And the last piece, why do we care about this, is testing theories. Just being able to explore the inside of the star and how stars evolve. One thing we always, when we're teaching in a introductory astronomy class, in a college introductory astronomy class, one of the things we always tell students, well, you can't watch a single star evolve. So this is a bunch of different stars and we plot the HR diagram. In the case of short period pulsators, that's not necessarily true. We actually have the potential of seeing stellar evolution happen right before our eyes. So that is a reason why we want to study these objects, to actually see if our stellar theories are correct. Are we getting the right timelines? Are they evolving at the right rates? And this works well with the Ariel in particular, works with the Cepheids, the Delta Scooties. Those are really the three main ones that we see a lot of this. And you're going to see some of this in some of the presentations that are coming. One of the things mentioned before, this idea of multi-periodic stars, so leading into Astro Seismology. Each cycle can be a different height. So there's actually kind of a beat frequency here. So we get a lower, then higher. And because of that, we can kind of tell these stars might have more than one frequency. And some have been measured, I think the record's somewhere in the neighborhood of 180 frequencies in a single star that from the Kepler satellite data. And that was and there's a unique pattern to those frequencies that gives us an idea of the internal structure of the star. So that's why the multi-periodics are really kind of fun to deal with in a variety of cases here, whether they're Delta Scooties, whether they're RLRs, they both provide some interesting patterns. And this is, the Astro Seismology is actually a place where white dwarfs are really studied, so a way to try to get an idea of what the inside of a white dwarf looks like. So there's a lot of astroseismology of the white dwarfs. Just really quickly on astroseismology, the idea here is if you look at this blue one off to the end here, we usually talk about pulsating stars and we make it always sound like the star goes all out together, all back together. So what we call a radial pulsation. That's true enough. But some of them, when they get a lot of frequencies going on, you actually get some different shapes to the pulsations, kind of one layer going out while another layer is coming in. And so this is an interesting thing. The challenge here and why it's nice to have an organization with the world covering ability of the AAVSO is that we can actually do these kind of and provide the data sets that are possible to go after things like this. There's aliases in the data that show up if you try to do this from a single place. And so you generally have to do this with a ring of observatories around one of the hemispheres. So this is a place where you could be asked to join in and help collect data to actually see which modes, which of these different ways of pulsating are active in a given star. So that's kind of a fun type project to do. So that, and there up, you look at the title here, this is actually the correct spelling, the E in here. The other thing, testing evolution. Can we actually see things change? For a long time, like I said, when we teach students, we say, no, you can't see a star evolve. And that's not really true. sometimes we see things in the period changes of these objects that tell us that evolution's going on. It's that probe. I mean, this is a problem with a star. We look at a star and we can't see past the photosphere. What's going on the inside? What's changing? The neat thing about short period pulsators, they are that window to the inside of the star that we don't have any other way. And obviously in RLREs, this is a way we can get that information. And so some of these things show very complicated period changes. And part of this with the legacy, the RLRE legacy program with the AVSO, this is something that is very important. Being able to monitor these things for extended periods of time and with a lot of coverage. So not just 1 year and 10 years later, but a lot of coverage helps define details that show up. So hopefully what that allows us to do is go on to the next couple speakers and actually show you some case studies related to that. So I will pass the time over there if I can get my, let me try to give control back here.
Thanks. Our next talk is going to be given by a combination of people. They are doing a summer research project with Richard Berry, and they are going to talk a little bit about what they have done so far on their project, which includes two specific variables, SX phi and XX Cygni. So as soon as, so you should be able to share your screen now, Nolan. Sorry about that. Perfect. And I will pass off the presentation to you.
All right. Well, that was a really fantastic introduction. Thank you, Doctor. You covered a lot of things that we're going to be talking about in our presentation. I am so excited and honored to be presenting to all of you today. My name is Sol McLean, and this is my partner, my presentation partner, Nolan Sodaway. We are both students from Wilson High School, as well as participants in this year's Pine Mountain Observatory Virtual Astronomy Camp. PMO is a wonderful annual tradition for our science department, wherein a group of upperclassmen get to do practical astronomy with a select group of astronomy mentors. This year, our camp was done virtually with students working from home with their mentors online. And Nolan and I had the privilege to get to work under Mr. Richard Berry, who's with us today. Our investigation over the 2 weeks of camp concerned variable star XX Cygni. We've got a lot of fantastic findings and results to show you, so let's get started. All right, so to start our inquiry, we had to look at what had already been done. Of course, there have been many, many studies of XX Cygni over the past 116 years since the star was discovered. Reading and reviewing the historical work of others helped prepare us to design our own investigation and find questions we could help answer. We've learned to read academic papers thoughtfully and critically over time, as well as how to extract meaningful information. Quite a few of these papers we used for reference. On top of literary sources, we also had the privilege to talk to Dr. Michael Joner and Dr. Joyce-Ann Guzik a few weeks ago about our research, and we got to ask them even more specific background questions. Their help was essential to providing us with this depth of understanding that we have now. To briefly review, in case you are unfamiliar with XX Cygni and need some background information, XX Cygni is a delta Scooty variable star, which Dr. Eric Heintz talked about a little bit in the Cygnus constellation. It's classified as a metal poor, high velocity, blue-white population 2 star, and is characterized by its unusual single mode pulsation, large amplitude, and long period for a star of its class, which is what warrants investigation in our case. Photometric observations have also revealed that period changes in XX Sig are positive, unlike other SX Phi stars. So we thought it would be worthwhile to look into pulsation behaviors of XX Sig with extension and greater precision in order to confirm a relationship between period change and stellar evolution.
The mission behind our project was to use modern technology to form stronger conclusions to be used by other scientists about XX Cygni and variable stars alike. As my partner talked about, the study of this star has been very historic, dating over a century, and with it, technology's improved. In the beginning of this star, image capturing would take minutes between images, but now we can throw CCDs into telescopes and get them every 10 seconds or so. And with this, combined with image processing software, we can get some really high quality data. So let's have a look at that data. It all starts in Alpaca Meadows Observatory. This is Richard's personal observatory and telescope. If you're wondering, it's an 11-inch Roe Ackerman Schmidt with an 8 horizon camera. Now, just a brief note, Richard has studied XX Cygni before with an 80 millimeter refractor, which means that if you're a teacher interested in studying the star, it's perfectly doable by this school. But back to the star itself, with this setup, we were able to take roughly 2,000 images a night. And let's dive into what those images look like. So here we have just one of the 20,000 or so total that we've taken. And at first, this was pretty overwhelming for me. You know, I've got 20,000 images of white dots on a screen. But as I got better at processing, I was able to better understand and better process this image. So what I'm going to do now is just walk you through the process of locating this star, because that's where I found my bearing. It all starts at this triangle in the top center of the screen. We draw a line across the hypotenuse and extend that to the next bright star. Then through an obtuse angle, we can look for the next bright star. It's right here. And with that star sandwich formed between that arrow pointed star and the obtuse angle star, we have XX Cygni. Now, the reason why we set up this star sandwich, so to speak, is because the bread of this analogy are our comparison stars. Now, once we have this located, we can dive into image processing. Now, we used AIP for Windows, the magnitude measurement tool. And if you're interested in the specs on our devices, our technology, they're right here. We didn't use a filter. We subtracted our dark and flat frames to get rid of any imperfections in the area and camera. And we used 2x2 binning because the 8 horizon is a colored camera. Now, once we had our data, we threw that into Excel where we could process it. Just a note, this is 31 of our 2,000 or so points total. Luckily, we have click and drag for highlighting. So once we have this and we have our night's worth of highlighted data, we can start processing it and extracting time of maximum. And how we do that in Excel is zooming in a lot and looking at the pixel steps. You can see how it's no longer a curve, but rather steps that form a curve. And we look for the top. That red line is and here's our process. So we follow the steps. We get our top, which is right here where that red line is. Then we get into a little bit of estimation. We say this star or this point right here is a little bit to the left. This point right here is a little bit to the right. So we average them and we get our time of maximum. Although this is pretty accurate because we're so far zoomed in, we can still do better. And that's what we're working on currently. Our assistant, Rispa, who was not able to join us today, is working on a better method of Excel that allows us to embed the process and have the computer program extract something for us. But still, this would require a little bit of manual labor. So we're also working on automating this process in R. In total, we're observing 2 values. That would be the time of maximum and the stellar magnitude of XX Cygni. And as you all know, even though this is just 2 variables or values, we can get a lot from this when we start graphing it. And my partner Sol is going to tell you all about that process.
So after we've transferred all of the raw data to Excel, it's time for analysis. Once the data is extracted from the FITS files and moved to Excel, we can tabulate and, in its most basic form, analyze it. The most essential of the values that we recorded was the time of maximum magnitude, here shown in heliocentric Julian days. We compared our observed values to a computed or theoretical time of maximum, calculated by using the epoch. In comparing the two values, called the O minus C, we could determine whether maximums were occurring before or after they were supposed to, therefore letting us know if the periods are increasing or decreasing. This is our data with the past 116 years worth of observations of XX Cygni. It's really interesting to look at the different collection sets in comparison. For example, if you see our data here, like other modern studies, we used a CCD camera to produce careful and precise measurements. Back here was a time of like classical photometers, photomultiplier tubes, and then all the way over here, we at the beginning, the data of XX Sig was collected by photography. It's really interesting to see the development of photometry develop so practically. Our data falls right in line with the trend of difference between the computed epoch and the observed one. You might take a pause at this more recent collection of red dots right here. Oh my gosh, Blake, we read your studies. I thank you so much for coming here. We mined all of the data out of the papers we read. Many of these points come from the IBVS. These more recent red dots here are sourced from Yang's 2012 studies references. So this is what our data looks like when we linearize and standardize the data, removing some of the more obviously erroneous measurements. Depicting a continuous steady rate, we were happy to find our evidence fits the continuing narrative that XX Sig is continuously changing. Using the data from Richard's past 11 years studying XX Cygni, we can observe a distinct decrease in the difference between the computed time and observed time of maximum. In the grand scheme of the star, that means that the star's period is actually increasing. Our data collection comes at a critical point in the evolution of the Delta Scooty star when it seems to be evolving towards a larger period. This could have great implications. Are we maybe seeing the star evolve off of the main sequence? Just over the course of this workshop, in 2 weeks, we were able to document 18 times of magnitude with the most absolute precision. If you look at the values here, you will notice how remarkably small our errors were. You take note of the individual pairs each night. Those were peaks recorded on the same night. You can recognize how standardized our data collection was. Differences occurring on the same night are within fractions of seconds of each other. We've added error bars here that represent uncertainty, but we can be confident that our computers are acquiring more or less exact data. The error bars might even be smaller, but their magnitude is driven by the discrepant point all the way there up at the top. As for that point, we've looked into it and we can't determine that it's actually erroneous or a problem in any way. It could be representative of something significant within XX Sig's period, but it also could not. For this, we've been using we've been using Excel's trendline functions to synthesize our data in this way. For a preliminary method, we're confident this is the best method of approximation. However, we are in the process of investigating further methods.
Although our data is arguably publishable raw, we'd really like to continue to analyze it to make it more of an asset to the community. And to do this, we're going to be using a couple programs. The first being the AAVSO's very own VStar. What's shown here is a phase plot, meaning an overlay of all of our 20,000 points so we can get a function for the period. Next shown is the period analysis, where we can look at overtones, analyze anomalies. We can already see an extra overtone that we're going to be looking into in the future. Now, some other methods that we're going to be using, shown here in ascending order of difficulty, just so that we can kind of work our way up in complexity and not have to dive into anything that we don't necessarily need to. Here we have first being data verification, of course, because we just want to figure out, is everything working as it should? Like my partner talked about, that anomaly point that we had, we need to make sure that that's in fact an anomaly and not simply an error. And we're going to continue down the line, hopefully figuring out other overtones and interesting points in the period with these methods of analysis. Now, in order to use these methods, we are mostly going to be using RStudio and R. If you're unaware, this is an object-oriented programming language that is used for data analysis. Now, the reason why we're using this, a language as opposed to a program, is because we have a lot more freedom in using this. While programs that we can download have functions already written for us that we can use, in RStudio and R, we're able to write our own functions and have more freedom in doing this. And we can look at outliers, try to get rid of them. And in doing so, this will increase our accuracy and certainty.
So our data is important in showing significant period changes as they occur, and the precision of our time of magnitude, maximum magnitude observations are useful for future investigations of XX Cygni. Of course, there are a lot of questions that we didn't get to answer. Either we didn't get the chance to explore these questions, they weren't the target of our investigation, or for another reason, they remain a mystery. Are the period changes of XX Sig sinusoidal or variable with time? There will always be still more work left to do.
Now, you may have noticed a sort of chronology to our presentation. We started out talking about our collection, then our analysis. And I'd like to sort of conclude that our presentation in the same sense. So it all began in Alpaca Meadows Observatory, where we collected our 20,000 images, got set up for the rest of processing. Currently, we're doing our processing and analysis, where we're using these tools and methods to better understand our data into forming conclusions, which we can use in the future to publish a paper or more, and hopefully present at another AAVSO annual meeting. Now, to end this presentation, I'd like to acknowledge a few people that have really made this possible. First being Richard Berry, our mentor, who owns Alpaca Meadows Observatory. He's guided us through this process. James McAteer, who has also been guiding us through this process. He wasn't able to make it today, but he's been serving as the sort of red team to poke holes in our case before we get to the peer reviewing stage of our paper. Dr. Joyce Ann Guzik and Dr. Michael Joner, both of whom took time out of their day to talk about the theory of this star, because it's really easy to get lost in the sauce of so many images and data, but they really helped us understand the star. Mr. Joseph Minato, he's our physics teacher who put on the virtual Pine Mountain Observatory. He makes a big difference in our lives, especially with this camp. And finally, the AAVSO, especially the short period pulsator section, for having us and allowing us to present here. Now, here's our references, so we show that we've got them, and maybe we'll have to pull these up for our Q&A section. Thank you.
Thanks, Nolan and Sol, for this very nice presentation. Next will be Jerry Simolik talking about the AAVSO Legacy Program.
Okay, let's get this thing running here. All right, the Legacy Program goes back to program stars that were selected back in the 1960s, 1970s. In 1967, Tommy Craig started a committee, we didn't have sections back then, dedicated to Cepheids. And about a year later, Marv Baldwin started a committee dedicated to RLI rays. Both of these guys put together groups of stars that we would study over the long haul, looking for changes in period. In 2008, the AAVSO Council reorganized the organization in sections, and the two committees were essentially combined into the section. Originally, they called it short period variables, but Dave Hurtis and I discussed that and decided that eclipsing binaries are short period variables, some cataclysmic short period variables, so we picked the name short period pulsator to be a little more specific as to what type of stars we're observing. One of the stars that we've got an excellent history on is XZ Cygni. This is an Ariel star. And this particular plot shows a number of light curves observed in the same observing season. You'll notice that the light curves have differences in brightness at maximum as well as phase at maximum, difference in brightness at minimum as well as phase of minimum, and the shape itself changes somewhat from cycle to cycle. This is caused by something known as the Blaschko effect, which is a secondary period. In this case, I think it's on the order of 57 days, where the star will cycle through changing the shape and amplitude of the light curve. And I also want to point this out because many of our observers focus primarily on observing the time of maximum. And I really want to stress that observing the time of minimum is just as important. I should say time, the light curve through minimum. In fact, the whole light curve is very important because when we do a analysis, we're going to do a Fourier transformation on this, and you like to have the whole light curve as much as possible. Because many of the light curves, or say the periods of the RLAs, are on the order of a half a day or so. Sometimes it's impossible to observe an entire cycle in one night, but I try to observe them as much as possible all night long and get as much as I can. You heard about a little bit about O-C diagrams. This is an O-C diagram for XZ Cygni going back to the beginning of the 20th century. In fact, these early observations were made by Blaschko himself. And you can see that the period had gone through a series of shortenings up until the mid-1960s, when there was a very dramatic shortening of the period. And that continued until about 1979, where there was an even more dramatic lengthening of the period. And since then, the period has been back to getting a little shorter every decade or two. This is probably one of the more dramatic cases we have of changes of period of an RLA star. There was a paper published in AJ back in '04 where Horace Smith and a number of his students analyzed the data on this star going back over the previous century and determined that in addition to the fundamental period changing, the Blaschko period also changed noticeably during this, particularly this event that took place in the 70s and 80s. And there's a copy of that paper. This is one of the goals of the Legacy program, is to watch stars for a very long time to understand what type of evolution is going on. Another example would be XZ Draconis. Again, we have significant changes in the brightness at maximum, some changes in the brightness at minimum. And again, this star has shown over the past, well, about a century worth of data now, that the period has been changing, although not nearly as dramatically as XZ Cygni, but there's still some significant changes going on. AR Hercules is a star that has, in my mind, a much more dramatic Blaschko effect. Not only does it change a lot more in amplitude, but we're seeing a lot more phase changes. Occasionally, it'll even go flat for an hour or so right at the top. And also, again, substantial changes in minimum. So this is a star that is very definitely worth study. And to show the O-C history, from the 1920s, the period was fairly constant. Something happened around 1950 where the period got dramatically shorter, then dramatically longer. Unfortunately, the observing community wasn't doing a very good job of monitoring the star. You can see the data, the times of maximum, are extremely sparse. So there's not really enough here to tell what had happened to the Blaschko period during those changes. This is really unfortunate, but there's no way we can recover what happened then. This is another reason why we want to have a legacy program that continuously modern stars so we don't miss these type of events happening in the future. TV Bo is also a Blaschko star, but this is a RRC as opposed to the RRAB, which I had been showing you. In this case, the Blaschko effect it leads to changes in the shape at the top, sometimes changes in the phase of the maximum, but not nearly as much change in brightness as we've seen on the RRABs. The RRABs, a much higher percentage of the stars exhibit the Blaschko effect, but there are a number of RRCs that also exhibit this effect. The O-C is not real exciting, but we do see there's been some subtle changes, and the scatter we're seeing is due to that Blaschko effect and the changes of phase of the maximum. One more RRL I'd like to talk about is SZ Hydra. This star is particularly interesting because it shows the light curve shape of the RRAB, but then at times it looks just like an RRC. This is what we refer to as an RRD, or dual mode star, where the star will be pulsating in its fundamental node. It'll switch to a first overtone, and then it'll switch back to primary mode, fundamental mode. And the O-C for this particular star, I've color-coded the times of maximum, where the blue are when it's in the RRAB mode and the red are in the RRC mode. And you can see that historically, it's always run a bit early when it's in the RRC mode. And there's also a significant change in period here, and then there's a much more subtle change in period that took place just a few years ago. We're just getting a good handle on what the period is now. We had heard a little bit about delta Scooty stars. There have been a number of those that had been included in the what was once called the Ariel program. SC Lynxus is a fairly regular star, very repeatable looking light curve. And what makes this particularly interesting is the O-C plot. You can see there's pretty much defines a sine wave. This is caused by the fact that the pulsating star is a part of a binary system. And as the stars orbit each other, the light travel time between the Earth and the star is changing. So the times of maximum will start running a little early as the star approaches us, and then later as it moves away from us. And this cycle has got a period of about 3.3 years, which would be the orbital period of the binary star. The fact that the star is a member of a binary does lead to some interesting additional opportunities, because when you have a binary, you can learn a lot more about the mass of a star. This is another delta Scooty that we've been observing quite a bit over the last few years. And in this case, you can see that there's quite a change in the brightness in one single night. There is a fairly constant fundamental period of somewhere on the order of 2 hours. And here's the data from a single season is plotted to phase. And you can see that the period is fairly regular, but there is a lot of variation in the brightness of the star, particularly at maximum. Now we can take that same data and plot it to a second period. In this case, we're a little over 3/4 of a day. And now you can see the individual pulsations, but you can see that there's this additional period that's modulating the brightness of the star at maximum. So there is a second mode going on here, even though there is a fundamental mode that tends to dominate. And the O-C for that is pretty much, at least over the interval we've been watching it, a straight line. And the scatter I'm going to attribute to the second mode of pulsation. You actually saw a light curve of this star earlier in the presentation, VX Hydra. We put together a project on this star about 15 years ago or more, where in addition to myself, we had Sean Dvorak was observing from Florida, Rudy Poklar was observing from Arizona, and Neil Butterworth was observing from Australia. And so in this particular light curve, you can see, I think this was Rudy's observations, and then Neil picked it up from Australia, and then Rudy got another night's worth, and unfortunately everybody was clouded out and then back again. And if we would have had an observer in South Africa, we could almost got continuous observation of the star, which was one of the goals we were shooting for. we observed quite a few different periods, quite a few different frequencies of pulsation. Two primary ones came out of it. And you can see that both of these, there is definitely a trend there. There is something of a light curve, but there's a tremendous amount of scatter within that light curve. In this case, we have two different periods that are, I'll say, almost equally dominant in the star. So what I did was took those two periods and I found a beat harmonic between the two. And at times the two periods will tend to cancel each other out. At times the two periods tend to reinforce each other. I will point out that when you get a star like this that has no single fundamental period, that using O minus C analysis becomes pretty much useless. So I don't even bother trying with it. You have to pretty much go to a Fourier type analysis. I'm going to close out talking about a few of the Cepheids. Now, we haven't really been very actively pursuing Cepheids within the section, but lately I've been trying to get some of these stars going again. The biggest difference in challenging observing Cepheids is that you can't do a whole lot in a single night because, as we saw earlier, the periods can run quite a bit longer. So the method of observing I use is to observe the star every clear night, and since they're a little more leisurely in their changes, I can hit it with all four of my filters. Then I'll do this for an entire observing season and then plot the photometry to phase to generate a light curve. This is one of the stars that I picked up this last winter. And in the corner, I've got a visual light curve published by Tom Craig in one of his reports, probably about 40 years ago. And what's interesting is that there is maybe a little disagreement in the brightness at minimum and maximum, but that could be attributed to the fact that we're using different comparison stars than he did back in those days. But the general shape of the light curve seems to be pretty much the same. Nearby is SVMON. Now in this case, you can see that in the old data, the observers were seeing a definite extra hump on the declining side of the light curve. And now I'm seeing that extra hump on the rising leg of the light curve. So over the last 40 or 50 years, something's changed. I don't know how much data we have of these in between, but this is another one of the reasons why we'd like to be able to observe stars for a long time, to look for these types of changes. TT Aquila is another one star that shows a similar effect. Here we have an extra hump on the declining side, and here we have a bit of an extra hump on the rising portion. So this is, in a nutshell, what we're doing with the Legacy program is trying to observe stars for a long time and see what kind of changes we can see. I think for those of us who were at the fall meeting last year in Las Cruces, Horace Smith gave a presentation about Cepheids, and he closed out by saying, if you want to do a 100-year study on a star, pick a star with 50 years of observing history and start when you're young. So what we're trying to do is provide that 50 years of observing history. And with that, I will send it back. If I can.
Thanks, Jerry. Always great to hear about the Legacy program and exactly how we're monitoring all of these stars. We will finish it up with another presentation by Dr. Eric Heintz.
Okay, let's see if we can go back to a screen share here. Okay. Okay, actually I was enjoying those talks, so I'm kind of maybe not prepared to come back quite so quick. So those are things I've been studying for a long time, and it's fun to see what's going on. But just a couple things, as you're interested in observing and trying to provide data for these programs, I think you could see the difference with the Cepheids and the RLREs. You know, how often can you take observations? it is an interesting problem. And this is also related to the big surveys that are going on right now. There are a lot of different surveys that are covering large chunks of the sky, or in the case of Kepler, small chunk of sky, but with a lot of observations. So one of the big, this is actually an era of time domain astronomy. It has become an in topic in astronomy right now to do variable star work or variable object work of all kinds. And so this is the era of the CCD has made this possible, and people look for a lot of different things here. The Kepler satellite obviously was looking for planets mostly from transits, but in the process it also found a lot of variable stars. It monitored a lot of variable stars at a specific rate of observations, actually 2 rates, 30 minutes and 1 minute, the original mission. And there have been some satellites that predated Kepler that were doing similar things. There was the MOST satellite out of the University of British Columbia and Corot out of France doing those same kind of projects, but they were targeted. They were at very limited number of stars. What we've gotten to nowadays is wide field imaging for a lot of things. So nearby asteroid, there's a project in Hawaii that is looking for the asteroids that are about to hit us. It's kind of a last alert system before the asteroid hits the Earth. But in the process, they've been finding a lot of new variable stars, in particular, a lot of short period pulsators. The Assassin program looking for supernovas is also doing a lot of that. And then another couple programs doing the transiting planets. KELT was a ground-based system for many years that found a number of very interesting transiting planets. And now the TESS satellite is doing even more of that work. And there's a lot of work on following those up. But the idea of following up on these objects, the KELT and the TESS, also leads us to following up on things from these other programs. And as we look to the future, we're going to have LSST coming and millions of alerts a night on new variable objects. There's a lot to follow up on. And there are other projects. I'm not, some of these are ones I become familiar with from a variety of reasons, and sometimes my students point them out to me. But as it says here, a byproduct of any of these big monitoring programs, like LSST is going to cover the entire southern sky and even into the northern sky a bit, maybe once a week, data points, something on, few days to week, an observation in that scale, but the entire sky. So they do discover new variables all the time, and they usually have some kind of intelligent system, some artificial intelligence system to try to classify these objects. But one of the big things, current things in astronomy, is a term called cadence. How often do you take observations? If you look at some of the data we've just seen on RLREs, Cepheids, Delta Scooties, if you're taking a data point a week on an RLRE, that's probably going to be a problem. You're not going to see the curve very well. It's especially true on Delta Scooties. Cepheids, maybe. And so a lot of these programs, they weren't designed to find the stars that we're interested in. And because of that, you can get some very interesting results. And what this comes back to in the end is being able to actually trust the periods that people find. One thing I'll say, I'll use Atlas as the example because I've been doing a lot of work on Atlas. I was chairing a session at the American Astronomical Society, and the speaker was talking about Atlas and discovering a new set of short period pulsating stars. And because we had a gap in speakers, I just turned to him and said, "Can I have all your Delta Scooties?" By the time I got back to my hotel room that night, he had sent me a list of about 300 or 400 delta Scooties, of which about 250 were newly discovered. I'm also looking through the Kelt archive. There's about 6,000 stars in there that are previously unclassified. But I don't necessarily trust the periods that they're publishing. Oops, sorry. For a couple things here. One is, as we've seen in a couple cases here, the multi-periodic nature of some of these objects. Trying to, if instead of getting these really nice curves like we just saw for the Arielaries and some of the Cepheids, imagine you're getting a data point on one curve, skipping a couple cycles, and getting a data point on another curve. And something is going crazy like this. How do you get a really good period estimate if you're not getting good complete cycles? One of the things that's come out of the Atlas data, we have a program here at BYU that has 4 robotic telescopes on our deck. We have almost robotic telescope in the dome, and then you've heard the name of Mike Joner brought up. He is our mountain observer, and he has telescopes on the mountain. We range everything from a 5-inch to a 36-inch. So we cover a wide range of these objects. And we've been looking at a lot of these Atlas targets to see if the periods they published are correct. One interesting problem we encounter, this last statement down here, one thing that happens with a lot of these multi-periodics, it turns out that the period they estimate, because they're picking up on different cycles, is a multiple of the real period. So like 3 times the real period or 4 times the real period. And that would definitely confuse, is this an Ariel? Is this a delta Scooty? And from an, if you want to use these as follow-up to study them in detail, you kind of like to know you're picking the right kind of object if you can. So to give you one example, this is actually what we call Atlas 70. It's just a sorted list, and we just numbered them in order. And this is the data from the 2 telescopes in Hawaii trying to pick up the asteroids. And they got a period of about 2 hours here. But you notice on a given night, maybe there's 4 observations. Maybe a little bit more here. This guy right here might be a better curve. And they also list this star as being monoperiodic. So it's only got the 1 frequency, not the beat frequencies that we were just hearing about. Okay. Well, what does it really look like? Well, let's take the best curve. Let's go back here and actually look at this, the night with the most data on a single night. And that's the upper left panel. So 5, 6, 7, 8, 9, 10 data points. That's the best piece of curve. This is the phase data of all the entire string. This is one night from our observatory upstairs. This was actually first light on our 24-inch. This was the first light curve generated by our new telescope. And so you can definitely see the difference here between getting a data point every couple minutes, every minute or so, versus a few data points on a night. And again, this is the best night they had. And we studied a lot of these stars all the way from, we've been looking at things, everything from about 6th magnitude down to about 16th magnitude. And the one thing we're finding is the higher amplitudes, they do okay. The lower amplitudes, they miss. And if it's got multi-periodicity, they miss the period. So the one problem that leads to is people will take their data set and plot it into an HR diagram using something like Gaia data as well, and make conclusions based on erroneous classifications. So there's a lot of problems with Cadence that can lead you to make mistakes about your stars. I'm going to show you a rather interesting one here. Okay, this is from the WISE satellite. Some of you might know this satellite. It's an infrared satellite that did a lot of good work, and then as the coolant, it had 4 filters, W1, 2, 3, and 4. And as the coolant left, we lost the W3 and W4 filters because they need cooling to get good data. And so they made a project called NEOWISE. You might not recognize that name NEOWISE as the one that discovered the comet just recently, the NEOWISE comet. This is the same mission. But they were doing some of the classic variable stars. Delta Scooties, Ariels, they're doing some really nice stuff. And so this is actually data from NEOWISE on, I'm not going to tell you what kind of star this is to start with, but so question here, just really quickly, I'm not going to have you answer it, but I'll walk you through this here. What would you guess the period of this star is at the right? Okay, it looks like a beautiful curve. I mean, that's a nice light curve. It threw me when I first saw it because it's not the shape I was expecting. But, okay, well, let's try to get a period here. Let's assume this looks like one complete cycle. So the leftmost point down here is at about 566.40.5. The one on the other side, 566.41.2. Well, let's just take the difference and make one cycle. Okay, that's about 0.7 days. So this looks like a nice RLR. It's not. Okay. This is because I pulled this specifically for a Delta Scooty. Delta Scooties do not go up to 0.7 days or almost 17 hours a period. This is DY-PEG. This is a good one for our group that was doing XX Sig. This is another one you might want to go back and do. This one's got some very strange period changes going on in it. So or if anybody else wants to jump on this one, it's a good one. The period of DY-PEG, the published period, 0.072926 days. It's got a period of about 105 minutes, which is about 10 times faster than the period we're estimating from this curve. What the heck happened? The cadence of the observations was 0.065, so about every 95 minutes per observation. It was very close to the same period as the actual period of the object. So each one of these points is roughly coming from successive cycles of the pulsation. And the timing was just right to just slightly shift from one to the next and generate what looks like a beautiful curve. The problem is DY-PEG is a fast riser, slow decay. So this looks like a slow rise to max and then a decay. DY-PEG rises fast and drops slow. So if I actually took this data and phased it with the period of DY-PEG, something interesting happens. This is all the data put together into one curve. So this is more than just the one night. But you can actually see now the faster rise and the slow decay. This is the classical shape of DY-PEG. But if you trusted the data, all the data you had from that program, you would have gotten the wrong answer. So cadence is a very important issue that we encounter when we start trying to do the short period pulsators. We have to plan ahead. So basically, when you're planning, when you get interested in some targets, and we're going to try to help with this on the web page for the SPP section, is to make sure we give you some idea of what is an appropriate cadence for a specific target to allow you to decide, can you provide data for that particular project? Don't want you putting your time into the best possible targets we can. And so this is one thing I always tell my students is that let the science dictate your observations. You don't take observations and then try to shove it onto your science. Start from your science, decide what you need, and then define your cadence from there. And as we prepare target lists, we're trying to, we have a very nice system right now on the RLR section that we've just heard about. We're going to try to expand upon that to give you a wider variety of targets. And in the process, also make sure we're telling you or giving you the information needed for the appropriate cadence level. What would be good? What do the scientists, what do the people trying to understand these stars need? So just really quick to finish up here is how to get involved with this. Basically, in a sense, almost any data is useful here. To give you an idea, so we are working to provide over a wide range of brightnesses and periods. So spreading out the targets, maybe going back to providing a star of the season so that a lot of people can contribute to a single object. And in that case, I'm kind of would prefer if we didn't do a single star, but kind of gave a range, provided Northern Hemisphere targets, Southern Hemisphere targets, and provided targets that are good on a 2-inch, well, I don't know about that, but up to, I know one of the local astronomical societies here, one of the amateur groups, actually has something like a 70-inch telescope. So I want to make sure there's targets for everybody, even on the really faint end. To give you an idea how valuable the some of this work is, I can tell you from what a paper I'm trying to push out the door right now. I was doing a lot of spectroscopy on another Cepheid called X Cygni. Not XX, this is the single X version. And this is a Cepheid that's been monitored for a very long time, going back again into the 1800s. And I saw something weird in the spectroscopy. So I basically pulled the entire data string from the AAVSO archive. You don't want to look at it, it's long. And the bulk of the observations are actually visual. So without camera, without just visual. And it turns out it's turned to be extremely valuable because we almost get, well, I would estimate probably 70% of the times of maximum light in the last 20 years have been picked up by this visual observing, and it's been very valuable. So there's a wide range. Now that takes a very experienced observer to pull that off, but with SLR cameras, CCDs, the beginning of CMOS, combined with telescopes of all sizes, we can provide targets of a lot of, over a wide brightness range, and ones that are critical. Talking about some of these with the RLRs, that gap. You know, if we'd had an observer in South Africa, that would have been great. The Astro Seismology, to try to eliminate some of the problems we have in analyzing the data, continuous coverage is very helpful, or not necessarily continuous, but actually having observers that provide a continuous longitude coverage so that as we put the data together, there's no aliasing in the data. So that is one of the big advantages here, is to have observers around that ring the Northern Hemisphere, ring the Southern Hemisphere, and some targets that are near the celestial equator. Great, everybody can hit them. So we're going to try to provide these and develop the SPP target list, try to give you some new possibilities to help with, and we hope everybody can join in and work and provide the biggest data sets possible to make the best results possible. So I think at that point, I guess we'll finish up here. So the idea of the SPP pages, I've changed a few things, or sent a few things in to be changed on the web pages, but there's a lot that needs to be done. Hopefully we'll get this, at least some of the rudimentary stuff up to you so that you can start jumping in and definitely contribute to the RLRE legacy program, and hopefully we'll give you some variety as well, to give you a wide range of targets to chase. So that's kind of where the plans are, and we look forward to seeing data from a lot of you contributing to this. Okay, I think that's where we're at, and I will stop sharing and send it back to headquarters.
Thank you, Eric. So at this point, we are now going to open it up to questions. And I will kind of weave my way through to try to get a sort of even distribution amongst people so that you don't have to answer question after question. The first question is actually a bit technical, but I will ask it and we'll see if there's a good answer. I believe this one is probably going to be for Eric. And this one says specifically that the energy output of a star rises with t to the fourth, but the peak value of the spectral diagram rises as t to the fifth, shifting t to the -1 to the blue, resulting in t to the 4 in energy. If you filter around the maximum in the spectral rise, is it actually t to the fifth?
Well, in this case, you're dealing with, if we just go back to the basic output of a black body, it's the r squared t to the fourth.
Right.
When we start looking at the pulsation cycle, you do have to account for the fact that we do shift the light around in the different band passes. So one thing that is important, I probably should have mentioned, sometimes times of maximum light studies, the O-C work, it can become filter dependent because the B maxes at a different point than the V, than the R. So the blue filters, green filters, red filters peak at different points. And so there is a relation. The brightness at a given wavelength is the r squared t to the fourth. But if you bring into account which bandpass you're looking at, it does shift it. So I understand what they're saying there. But the actual output is r squared t to the fourth.
Cool. We have a question specifically about T0. There are actually a couple, so I'm going to combine them. And I will, I believe this is for Nolan and Sol. And it's specifically, it's a question about essentially, where do you choose T0 from? In order to calculate the cycle number. And the follow-up is, if you took a different T0, would it change your O-C diagram?
Nolan, do you want to take this one or should I?
You've been dealing with O-C, but I will say that at least the cycle number is fairly arbitrary.
Yeah, that's pretty much what I was going to say. So T0 has been the first cycle number, has been more or less used. Richard, feel free to jump in if at any point I'm getting this wrong, but it's been pretty much the same. Studies have been using the same one over and over again, but it is more or less arbitrary. For example, when we were doing our graphs of our more recent studies, we decided to place T0 0 epoch at a more recent time so that we weren't dealing with numbers in the tens of hundreds of thousands, huge numbers. Yes, heliocentric Julian days. If this isn't making sense, I'm sorry. It's probably something with my explanation. It makes sense to me. More or less, to put it as simply as I can, it's more or less arbitrary.
That is correct. So yes, that answer is perfect.
If I can make a comment about that, if you change T0, it can shift an O-C diagram vertically, but it will not change the shape.
Yes, exactly. And the shape is what we're looking at, so.
Correct.
This question I think is mainly directed towards Jerry. And it says, do Cepheids have long time periodicity? And I think what they mean is, is there an overarching period to the Cepheid outside of its typical cycle? So do Cepheids change period over time?
I've always heard that they do, but I'm actually kind of new at Cepheids. I've been doing them for less than 10 years. It's not like the Ariel that I've been doing for over 40 years. As I showed, there are some changes in shape of light curve over time, and I have seen other studies where the periods do change over time also. I really haven't delved into it real far right now. Although right now I have been in contact with one of our members from India, who, by the way, is viewing our presentation here. And he is interested in analyzing Cepheids over along many decades to look for period changes. So we'll see what develops from this project.
So this next question is for Eric, I believe. And they say, is conversion to HJD of sufficient accuracy for period determination, or does it need to be corrected to TCB as the Gaia observations are reduced to? I'm actually not familiar with TCB.
Well, this is kind of depends, again, it's sort of the period that we're dealing with on the star. So the long period stars, the HJD correction doesn't really come into play too much. Cepheids are long enough that the correction is washed out in a sense a lot of times. But as we get down the the delta Scooties in those short periods, then the HJD comes in. The one thing you can do beyond that, and something that you see quite a bit with TESS, Gaia, and some of the other ones, is going to the barycentric Julian day instead. So instead of the center of the sun, the center point between the Earth and the sun. It's a subtle correction, but it is used by the people that model multi-planet systems. Usually we're okay on the delta Scooties to HJD. If you're getting down maybe to the white dwarfs, you're probably thinking about maybe going to BJD, being that step down. But that's probably don't need it beyond that. I should say the error of the measurement for the time of maximum light is worse than that.
Cool. So this question, I believe, is either for Jerry or for Sol and Nolan, whoever wants to take it. It says the temperature of the star changes as well as its brightness. Does not the time of maximum then depend upon the filter to some extent? Could that not affect the times of maximum and thus the O minus C diagram results? So in other words, if you have periods, or if you have light curves in different filters, they could have different times of maximum. So if you combine those, would that affect your O minus C diagrams and the results from them?
That is possible. Now, I do know when I publish times of maximum, I do include the filter used. So that is part of the record. As far as the O minus C diagrams that I've been working with, that's almost overwhelmingly done with the V-band filter. So I really haven't run into a situation where I've dealt with other band passes. Of course, when I combine that with the visual, the uncertainty of the visual measurements is probably on the order of being high enough that it's not really going to make a difference. I think on a typical CCD light curve of an RL array, the best we're going to do for a error estimate is maybe a little bit under 0.001 day, maybe 0.0008, something like that.
Okay, the next question is for Eric. It says, can you describe a bit more the odd feature in the X6 spectroscopy and offer maybe some suggestions for the spectroscopists in the audience, targets, purpose, things like that?
Yeah, I can mention a little bit. Try not to give away the paper too much, but we're monitoring X-Sig with a really broad spectra that covered H alpha to H beta, and applying getting an H alpha index that's modeled after the classic Crawford H beta index. And everything was going along beautifully until about 2013. And the H alpha index dropped, and if you assume it was a temperature difference, it would say that the star dropped about 200 Kelvin on the surface. Just shifted in the star. Now going back through the AAVSO archive, there's a little funky shift in the data at that point. If you look at the data before and after, there's a subtle difference in it. And so it's, from the spectroscopy, it was this drop in the H alpha index, and it was slightly out of phase. So it was kind of both. So that's the spectroscopy change.
Okay, so the next one is a comment more than a question, but I will just read it out. It says, in addition to the LSS, I believe LSST, quoted, there is a targeted program called the Next Generation Transit Survey. They have just released they just had their second data release containing around 600,000 stars with 13-second cadence. I'm not, he says that he's not clear if they have avoided variable stars in particular, but their data might be worth checking out for anyone who is interested in data mining.
Yeah.
And that's interesting to me because I have never heard of this either. My one question I wonder about with this in particular is 13-second cadence for how long? So was this just over specific transit cycles, or did they keep the 13-second cadence for single nights? I'm kind of curious where they focused this particular information. There's a question now for Jerry in regards to specifically TT Aquarius. He said that there is an extra hump that seems to migrate throughout the light curve. Is there a theoretical explanation for what might be going on to cause this sort of change?
That I don't know. Like I say, I'm relatively new to observing Cepheids, and I really haven't delved into the theory.
Yeah, I must admit that I don't really know either. Typically, when you see a feature like that moving, it means that for some reason it's changed phase with respect to the other frequency for some reason. So that's a difficult question to answer without knowing a little bit more about the star in question.
On RR Lyrae, we'll often see an extra hump like that that has to do with a shock wave going on during the pulsation, but RR Lyraes pulsate in different modes than Cepheids. Cepheids are purely radial, so I'm not quite sure what causes that.
This is a question for pretty much the entire panel, and something that, which is that has an RR Lyrae ever been found to be in a binary system? I assume the answer has to be yes. But I don't know of any, and I don't specifically know of any eclipsing binaries, which are also RR Lyrae stars. Does anybody know of one?
I'm not aware of an RR Lyrae. I did mention the Delta Scooty. that is part of a binary system, although that's got a very low inclination and it does not eclipse.
Yeah.
There are a couple of delta Scooties that eclipse. YCAM does. That was a paper by Eloy Rodriguez. And there's a second one, I want to say it's YZCAM, that is an eclipsing binary with a pulsator. We love those. Those were actually some all Earth campaigns to do those because you can get the mass of the delta Scooty out of the binary system, especially from an edge on. And from that, then you've confined one of the parameters of your model. So those two are very substantial teams that were needed to assemble to pull that off. So they are really cool when you can find one, but I don't know of an RLRE that's like that.
Yeah, I don't know either. I have seen plenty of delta Scooties in particular in binary systems. There are quite a few Kepler papers about various ones that exist.
Yep.
Uh,
Actually, you want to see the worst one is there's one of the transiting planets from the Kelt program that's orbiting a delta Scooty, and they can't figure out the planet because of the stupid star.
For those of us who are more star people than planet people, I feel like they might disagree with the way that you put that, but I can understand how planet people would say it in that particular fashion.
Yeah, I'm on the variable star side. I'm on the pulsator side. I favor the star too.
But yes, I have plenty of exoplanet people who have similar critiques, if you will. So here's a different type of question. It says, for those of us who like to observe with binoculars, are there any targets we could contribute to with observations, considering short period pulsator stars, and specifically, how can we engage beginners into this area?
Well, there are three very bright Cepheids that can be seen, even naked eye if you're in a dark enough sky: Delta Cephei, Eta Aquilae, and Zeta Gem.
We should definitely consider that. We'll probably, one of the things we want to do is come up with a target list for the SPP section, something that we've been working on quite a bit. So it would be nice if we could separate that based on sort of magnitudes, so that people have a better idea of what stars would be good for them in particular to observe. And Sebastian says that there are two eclipsing RRC system or RLI systems from the Ogle database that exist in VSX. One is in Sagittarius and one is in Scorpius, but they are very faint, 16th and 17th magnitude. Okay, I guess not very faint, but on the fainter end. There's a question, can any of these stars be measured without using a filter? I'm assuming the answer is, of course they can. I think in general, you probably want to use a filter, unless you're observing with your eye, which is just another type of filter. And so that you can compare it with other people's data. That's kind of the reason why the filter tends to become very important.
Actually, I'm a big fan of using filters because I've run into problems with, well, more with eclipsing stars, where I've had variable atmospheric extinction if my comp and my check star are different spectral types, and the star is low in the sky. You find that the absorption of the red and the blue stars is considerably different, and it can affect your light curve.
Yeah, that definitely makes sense. There's a question largely for Eric. It says, to avoid the aliasing problems, would it be worth sampling the magnitude with a pseudo-random cadence?
That is actually sometimes done. The aliasing that really gets us is gaps. So if, when I mentioned YCAM, we had assembled a Northern Hemisphere team so that it was technically covered at all times. If one of the pieces had been missing and you had continuous viewing and then a gap and then continuous viewing and a gap, that gap is still in the data. So you actually have a 1 day period, unless you can have the coverage, no matter how you sample, if there's a gap in it, you've induced another period into the data. But the idea of kind of randomizing the cadence a little bit can take care of some of the other aliasing. So it doesn't take care of the big one, but it does take care of some of the littler stuff.
So there's a follow-up on the Next Generation Transit Survey. It says the telescopes are located at the Paranal Observatory in Chile, and they have concentrated on the cool end of the HR diagram, K and M stars. So might be too cool for short period variables. That tends to be true, although you could get cooler Cepheid stars, but I'm guessing they avoided supergiants and giants because they'd never be able to see planets around large stars like that. So that would be my guess, is they also avoided evolved stars, which is a little bit unfortunate, but I mean, for a transit survey, it's not uncommon. And that is all the questions, save one. And I'll let Eric decide if he would like to do this or not. It just says if time permits, he was wondering if you could go over some of the more technical details that you skipped or skimmed earlier in your presentation.
I can pull that back up. Let me go. If you want me to, I can. Wouldn't probably take a couple minutes to walk through it, but it wouldn't be too bad.
Mm-hmm. Do you have anything in particular that you wanted to hear about, Bill? Just to make sure that we're not, that we answer things effectively. I will stop share so you can pull up your presentation again.
Or he can email me later and I can send him more details.
He specifically said, what is the key takeaway?
Okay, let me just pull it up really quick, and I don't know if I'm going to have a key takeaway here. Let's see, did I get that up? Okay. Did I manage to get that back on the share?
No.
Okay, then let's see. Okay, there we go. Wrong button. Now we got it. Okay, so let's take a look at this really quick. So basically the main takeaway here is normally the idea would be that if we had high opacity, we would get this pulsation cycle, and that goes back to Sir Arthur Eddington actually gave us the first model of pulsators, the first idea behind it, but the problem was it was partially off because under compression the gas wouldn't do what we need it to do. It would tend to go up in temperature, and that would eliminate the the effect we want here. So the idea here is if the gas is compressed, so what we're looking for is an area of partial, so the gas at a given level of a particular type, so hydrogen, helium, whichever, depending on the pulsator, it's partially ionized, and because of that, under the compression, the heat that's generated from the compression goes into ionizing the gas instead of the temperature going up. And what this does is it drives the density up. So the density is going up without the temperature going up too much. And that provides the process by which we can dam up the energy that's trying to come through the star, so that it increases the opacity, and that's what leads to the block. So what we needed was to increase density without increasing temperature, and that's why this happens in an ionization zone. And then the same thing's true as we expand the target or expand the star, reach a point where we start getting recombination. So energy, extra energy goes into recombination. That makes the material become transparent, the light can go through, and then gravity pulls down. So basically, Eddington had it mostly right, which is what we would call the kappa mechanism, if you look that up. But we need the kappa gamma to actually generate what we actually see in the stars. And that's just the base pulsation. There's a lot more to it for the non-radial, but this is the basic radial piece. Hopefully that was even marginally understandable.
Astro Seismology is a very complex subject. There are books written on it. I took an entire class on it. So, and it varies a lot from star type to star type. But it looks like that is all of the questions that we have so far. Thank you all for coming and attending this webinar. We really appreciate it. A special thanks again to our sponsors, Voice Astro and H8 Cameras. We have a survey following this. We really appreciate the feedback. I know a lot of you have probably done it multiple times now, but we look at every single one of these and we use them to improve for future webinars. So if you have any thoughts, please fill out the surveys. We really appreciate it. And with that, I'm going to close. I hope everyone had a good time. If you have any more questions, feel free to contact the AVSO, go to the SPP section page, and we hope to see you in the following webinars. Next week will be the photoelectric, we'll be on photoelectric photometry and observing. Okay, thanks everyone.
Well, that was